Why does the universe seem to expand faster than light can carry its stories? You learn that nothing outruns light, yet the cosmos stretches away from us so quickly that entire galaxies fade into unreachable silence. How can light be the ultimate speed limit, and still not fast enough for the universe it inhabits? It's a contradiction that sits quietly beneath everything you've ever heard about the cosmos, an unanswered whisper that deepens the night around you as you begin to wonder what light is truly racing against. Welcome back, traveler. Tonight, we drift through science. You're here, in your own quiet space, maybe lying on your bed, feeling the softness of your pillow holding your head, or sitting back with headphones as the room dims around you. The world outside is finally slowing down, and if this kind of calm, late-night science helps you rest or feel less alone, while the universe keeps expanding in every direction, I'd be grateful if you left a like and subscribed. It helps this little corner of curiosity stay lit for others wandering through the night. If your thoughts are heavy or scattered right now, that's okay. Maybe you came here because sleep feels distant, or tomorrow feels too close, or your mind refuses to quiet itself. Whatever brought you here, you don't need to follow every detail. You don't need to understand every term or visualize every idea. You're allowed to drift in and out, to let your attention soften, to rest without holding on tightly. This is a place where curiosity can soothe instead of overwhelm. Tonight, we'll explore why light, this thing we're taught to imagine as unstoppable, is constantly falling behind the universe it tries to illuminate. We'll walk through cosmic expansion, through the strange behavior of space-time, through telescopes that strain to catch the last photons from fleeing galaxies. We'll step into laboratories where scientists calibrate lasers, chase microsecond timing errors, and uncover how fragile the measurement of light really is. And we'll trace how human hands, machines, and mistakes all shaped the way we understand the universe's impossible speed. So as you shift slightly, settling deeper into where you are, feel the night soften around you. Nothing here is urgent. Nothing needs to be solved. Tonight we'll move gently through a story where light tries to keep up with a universe that refuses to wait, and gradually, you'll begin to see why the cosmos outpaces even its brightest messenger. Let the darkness feel familiar, and let your breath steady as we step quietly into the first stretch of this journey. You lie in your quiet room, feeling the softness beneath your body as you imagine yourself floating far from Earth, suspended above a slow-turning galaxy. Light spills from billions of stars, racing outward in every direction, each photon carrying a tiny sliver of cosmic history. Yet even as this radiant storm rushes past you, there's an unmistakable sense that it's struggling to keep up, that the universe is pulling ahead, stretching farther, faster, leaving the glow of its own stars behind. In school, you're told that nothing outruns light, that 299,792 kilometers per second is the ultimate speed limit, but this limit belongs only to things moving through space. The universe, in its vast and quiet defiance, doesn't move through anything. It stretches itself. It expands. The fabric beneath galaxies grows wider, like ink spreading across water. And because light must travel inside this stretching fabric, it finds itself pulled, thinned, slowed, not in speed, but in reach. Imagine shining a flashlight across a room while the room itself grows larger every second. Even if the beam moves at its fixed speed, the walls keep retreating faster than the beam can reach them. That's what the universe does on cosmic scales. It isn't that light slows down, it's that space outruns it. Light is loyal, consistent, steady, yet it serves a master that never stops pulling away. Measurements of distant galaxies confirm this stretching. The Hubble Space Telescope revealed that galaxies farther away from us move faster than those nearby, and farther still, they recede faster than light itself. Not because they're breaking physics, but because space-time beneath them is expanding so quickly that even light can't bridge the growing gap. This discovery shook our understanding of distance, time, and what reachable truly means. Human experiments began with simple glass prisms and evolved into complex observatories perched above deserts and islands. Scientists had to correct for atmospheric wobble, dust on lenses, and thermal distortions in mirrors. They learned to measure redshift, the stretching of light into longer, redder wavelengths, as galaxies drifted away. Every correction, every recalibration whispered the same message. The universe is expanding faster than the light trying to describe it. You picture a scientist late at night, sitting beside a humming server stack, examining spectral lines from galaxies billions of years old. Some lines, once sharp and blue, now appear faint, smeared, stretched. They carry the fingerprints of cosmic expansion, reminding the researcher that the light they study isn't just old. It's tired from being pulled across a universe that never stopped growing. This stretching gives rise to a haunting realization. The night sky is full of stars whose light will never reach us. Entire regions of the cosmos are slipping beyond our horizon, falling into a kind of cosmic silence. Their photons begin a journey they'll never complete. You imagine those photons like runners sprinting across an ever-widening stadium, their finish line moving faster than they can chase it. The James Webb Space Telescope revealed galaxies so distant that their first light left them over 13 billion years ago. But even JWST sees only a fading ghost of where those galaxies once were. Today, they exist far beyond the reach of light, retreating into a portion of the cosmos permanently cut off from us. The universe isn't just big, it's becoming unreachable. You feel a quiet sadness in that thought. Not a painful one, more like watching a ship drift slowly out of view, knowing it will never return. Light tries to show us everything. It brings the stories of stars, the secrets of dust, the glow of ancient collisions. But the universe expands without sympathy, pulling entire histories beyond light's grasp. Cosmological simulations try to recreate these receding horizons. Supercomputers crunch through billions of particles and trillions of data points, calculating how space grows over time. Technicians watch glowing pixels swirl into galaxy clusters. When they zoom out, the clusters drift apart faster and faster. The simulation ends with great islands of matter fading from each other, leaving behind a future where each region grows increasingly alone. The metaphor that forms is simple and devastating. Light is like a messenger running across a bridge that lengthens with every step. No matter how fast the messenger runs, the bridge always expands slightly faster. The message becomes delayed, stretched, softened. And eventually, the messenger loses sight of whom they were running toward. Yet light remains loyal. Even as the universe expands, it continues to move at its constant speed. It doesn't complain. It just keeps going, carrying whatever history it can. Old starlight, ancient explosions, the glow of the first atoms forming. You imagine those photons brushing past your cheek like warm dust, reminders of places you'll never see, but are still connected to through their journey. The deeper truth is that the universe doesn't treat light unfairly. It simply follows a rule that feels poetic in its cruelty. Expansion accelerates. Dark energy and invisible pressure pushes galaxies apart faster over time. The more space expands, the more dark energy there is to expand space even further. It's a runaway process, and light becomes an unwilling participant in a cosmic race it can never win. Scientists measure dark energy using type Ia supernovae, exploding stars that serve as standard candles. Teams travel to mountaintops, spending cold nights aligning massive telescopes. They compare brightness, distance, and redshift. And when they mapped these relationships, they discovered something stunning. The universe wasn't slowing down, it was speeding up. Light wasn't just late, it was falling hopelessly behind. You're reminded of moments in life when something moves ahead faster than you can catch it. A dream, an opportunity, a version of yourself you can see but not reach. Light experiences its own version of that emotional truth, forever chasing galaxies that once seemed close, but now slip further away with every heartbeat of the cosmos. Yet despite this, every photon that reaches us still matters. It still tells a story. It still illuminates a piece of the universe's past. The growing darkness isn't a failure. It's a record of motion, a signature of expansion, a quiet reminder that we are witnessing a universe in transition. As you lie there, the thought settles in gently. Light isn't inadequate. It's simply honest. It travels at a fixed speed because the laws of nature demand consistency. The universe, however, isn't consistent. It evolves, it stretches, it accelerates. Light isn't fast enough because the universe refuses to stay still. A new question forms in the dimness around you, not one of speed, but of meaning. If the universe is expanding faster than light can reveal it, what does that say about the limits of what we can ever know? And if light can't keep up, what does that make us, who depend on it for every glimpse of the cosmos? That question lingers softly, like a dim star whose glow hasn't reached you yet, hinting at a deeper layer waiting just ahead. You settle deeper into your pillow as the night around you grows calm, and you picture yourself drifting through a region of space where galaxies appear faint and stretched, almost as if they're being pulled apart by an invisible tide. The stars look distant, not just in space but in time, like memories dissolving at the edges. Light leaves them faithfully, but the fabric carrying that light stretches underneath it, thinning the glow until it feels like a whisper traveling through an ever-widening silence. It's strange to imagine space-time not as a backdrop, but as something alive in its own quiet way, flexing, swelling, drifting. Einstein first revealed that space and time aren't separate, but woven together like threads in a delicate fabric. And this fabric doesn't sit passively. It bends around mass, ripples with energy, and expands with a persistence that feels almost intentional. Light, fast as it is, remains a passenger on this moving surface. You imagine dropping a pebble onto a sheet pulled tight by many hands. The sheet shakes, vibrates, swells. Anything sliding along it, no matter how quickly, must follow its shape. That's what light experiences, not resistance, not friction, but obedience to a shifting geometry. It never slows, yet its path lengthens. Its journey stretches as the universe stretches, and across billions of years, those stretched paths become entire histories lost to unreachable distances. Measurements of cosmic redshift show this stretching in action. The farther a galaxy is, the faster it appears to recede. Not because the galaxy is moving through space, but because the space between you and the galaxy is growing. When light travels through expanding space-time, its wavelengths stretch as well, shifting toward red. Some galaxies are so distant, their light is stretched into infrared or microwaves by the time it reaches Earth. JWST was built specifically to see these stretched wavelengths. You picture engineers assembling JWST's segmented mirror, polishing each surface to atomic precision. They wear sterile suits, speak softly, and move slowly, as if aware they're crafting a device meant to chase the faintest remnants of ancient light. Every adjustment, every test, every recalibration acknowledges the same truth. The light they seek has been running across a treadmill that moves beneath it faster than it can compensate. In daily life, it's easy to imagine light as instantaneous, something that reveals reality the moment it appears. But on cosmic scales, light becomes a storyteller burdened by delays. What you see is never the present. It's always a record of something the universe has already left behind. Even the moon appears as it was a little over a second ago. The sun, 8 minutes ago. Distant galaxies, billions of years in the past. You imagine this delay as a soft echo layered across the night sky. Every star's glow is an old message, traveling faithfully across a changing universe, but some messages never arrive. Not because they're weak, but because space-time accelerates away faster than the messages can cross it. Those stories remain unspoken, sealed behind horizons that grow farther with every cosmic moment. Cosmologists call these unreachable regions causal boundaries, zones of the universe isolated from us forever. Nothing inside those regions can affect us, and nothing we send can reach them. It's not a technological barrier, but a geometric one. You could build a flashlight 1,000 times stronger, a spaceship 1,000 times faster, and still the boundary retreats as you approach it. Particle accelerators like the LHC help researchers understand how space-time behaves under extreme conditions. Physicists smash protons together, analyze spray patterns of particles, test how energy curves space-time at microscopic scales. They check for deviations in light's behavior, search for new particles, and refine models of cosmological expansion. Even here, beneath the ground in tunnels lined with magnets, scientists glimpse the same story. Space-time controls the rules, and light simply plays by them. You might imagine space-time as a vast stage whose floorboards continuously slide outward. Light are the actors sprinting across it, but the stage expands faster than the actors can run. No matter how energetic they are, no matter how early they begin, some scenes remain forever out of reach. And this isn't a malfunction, it's part of the design. This growing distance leads to a phenomenon called cosmic event horizons, boundaries defining which events can ever influence you. Beyond these horizons, light is stretched so severely that it never reaches observers. Cosmologists map these horizons using supernova brightness, microwave background patterns, and baryon acoustic oscillations. The data reveal that the observable universe is shrinking in influence even as it grows in size. You imagine these horizons as gentle curtains drifting outward, not harsh barriers but quiet veils. Behind those veils are galaxies full of stars, planets, collisions, and stories. But their light, no matter how bright or persistent, grows dimmer and dimmer, stretched into silence by the unstoppable expansion. Light isn't failing, it's being outpaced by the canvas it tries to illuminate. At mountaintop observatories, astronomers sit in dark control rooms, watching distant galaxies faintly flicker on their screens. They correct for atmospheric distortion, subtract noise, and calibrate detectors cooled to near absolute zero. Every photon captured is a victory, one more survivor of a journey across expanding space-time. These scientists aren't just studying light, they're studying what light loses on the way. There's a quiet melancholy in realizing that the universe hides more than it reveals. But this hiddenness isn't a flaw. It's a feature of reality's architecture. Light gives us a window into the past, but the future of the cosmos lies behind a curtain that light will never lift. That truth makes every photon that reaches you more precious, more fragile, more miraculous. As you lie there, you sense a strange companionship with those photons. They too travel through a world that constantly shifts beneath them. They too try to reveal a truth that keeps changing. Their journey mirrors the human experience. We move through lives where the ground shifts, where distances widen, where some things drift too far to reclaim. Yet even in this shifting universe, light continues to try. It continues to bring what it can. Every photon that touches your eye is a survivor of a race against expansion. And that persistence becomes its own kind of beauty. a reminder that even in a universe that outruns its own illumination, the stories that reach you are still worth hearing. And just as that thought begins to soften inside you, another question rises quietly from the edges of your imagination, one that wonders not only how light falls behind, but what happens to the stories that never reach anyone at all. A question waiting gently for the next turn of this journey. You rest there in the quiet, imagining yourself suspended at the edge of a colossal void, a region of space so vast that even imagining its size feels impossible. Galaxies glitter along the far boundary like faint embers, their light drifting toward you through oceans of dark. Yet the void expands quietly beneath everything, lengthening the path those photons must travel. Light moves at its unwavering pace, but distance keeps rewriting the rules, widening faster than illumination can cross it. Astronomers call these immense regions cosmic voids, though they're not truly empty. They contain wisps of matter, thin gas, dark matter scaffolds, the occasional wandering galaxy. But compared to dense clusters, they're deserts in a universe of forests. Light crossing these voids experiences something subtle. It gains ground, but the void gains more. It's like running across a meadow that stretches slightly with each step, a race whose finish line pulls away imperceptibly but relentlessly. To measure these distances, scientists use standard rulers, the most famous being the Baryon Acoustic Oscillation Scale. These oscillations, frozen sound waves from the early universe, left behind a preferred spacing in galaxy distributions. Surveys like DC and Euclid scan the sky, mapping millions of galaxies to detect these patterns. And from their spacing, researchers calculate how fast the universe expands. Each calculation leads to the same answer. Expansion keeps accelerating. Light is trying. Space is simply trying harder. You imagine a researcher in a dim office scrolling through maps of galactic positions, the shapes of clusters forming constellations of data. They zoom in, annotate, compare, rewind simulations, debate tiny statistical errors with colleagues. They chase not the galaxies themselves, but the spaces between them, the very gaps that make light's job impossible. Those gaps grow because of dark energy, a mysterious force that behaves like the opposite of gravity. Instead of pulling things together, it pushes them apart. Dark energy doesn't weaken as space expands. It amplifies. The more space there is, the more dark energy exists to stretch it further. The universe becomes a self-accelerating tide, and light becomes a swimmer caught in waters that always speed up ahead. You might picture dark energy not as a force but as a mood, an ever-present quiet insistence. It doesn't roar or explode. It's a soft push, relentless and patient. Over billions of years, that gentle nudge becomes a runaway drift, and light, no matter how loyal or swift, can't compensate for a universe expanding beneath its feet. Even the cosmic microwave background, the oldest light we can observe, bears the scars of this expansion. Originally emitted when the universe was just 380,000 years old, its photons have stretched so dramatically that they now appear as microwaves, cooled to just 2.7 Kelvin. Instruments like Planck detect this faint glow, mapping slight temperature differences that reveal the universe's earliest structure. But the very fact that this light is microwave instead of visible shows how far it's been stretched by space-time's relentless widening. Imagine holding a rubber band with a tiny mark in the center. Stretch the band slowly. The mark stays the same, but the band around it thins, weakens, and widens. That's what happens to photons crossing expanding space. Their energy dilutes. Their wavelengths lengthen. They fade not because they lose strength, but because the universe demands it. In laboratories, physicists mimic these redshifting effects by manipulating photons in waveguides or optical fibers. They stretch pulses, alter refractive indices, and watch the light elongate. These experiments don't reproduce cosmic scales, but they capture the spirit of the phenomenon. A pulse sent through a stretching medium returns changed, still itself, but carrying a memory of the journey's difficulty. You sense something deeply human in this. The idea of setting out toward a goal only to watch the distance grow faster than your steps. Light isn't weak, it's steadfast. It keeps moving even when the horizon slips away. And that persistence becomes touching, almost emotional, when you imagine entire galaxies watching their own starlight outrun by the expansion around them. Astronomers sometimes speak of the cosmic light cone, a diagram showing what regions of the universe are visible to us. Over time, this cone narrows backward, cutting off more and more galaxies. Regions that were once within our cosmic reach drift beyond visibility. In the far future, observers in our galaxy will see only the Milky Way and its neighbors. Everything else will fade into undetectable darkness. You picture yourself living in that future cosmos, looking at a sky nearly empty, unaware of the vast universe that once existed beyond your sight. It evokes a peculiar sadness, like inheriting a world with most of its stories already lost. The universe becomes a quieter place, not because it shrank, but because its expansion muted the voices of distant galaxies. Yet even now, while we're still in a time rich with starlight, we sense the fading. Astronomers track galaxies that are slipping away faster than the speed of light relative to us. Their photons fall behind, unable to compensate for the accelerating drift. These galaxies aren't dying, they're becoming unreachable, sinking beneath a growing cosmic horizon. In supercomputing centers, researchers simulate this future. They watch galaxies separate in slow, graceful motion, the voids between them swelling like deep breaths. The simulations end with isolated islands of matter drifting in darkness, and though it looks lonely, it's also poetic, a reminder that impermanence is baked into the universe's design. You imagine those galaxies sending out their last visible photons toward us. Not goodbyes, but remnants of presence, soft statements saying we were here. Light tries to translate their existence across expanding space, but some translations never arrive. And that's not failure, it's the nature of communication in a universe that never stops moving. Reflecting on this, you begin to feel a new dimension to the original question. It's not just that light isn't fast enough. It's that the universe doesn't require it to be. Expansion isn't an obstacle. It's a story shaping what we can know, what we can see, and what remains forever beyond our reach. As this realization softens in your mind, another thought approaches quietly, like a distant glow stretching across the horizon, suggesting that to understand light's limits fully, you must look not only at distance, but at how gravity bends the very roads light must travel. A thought waiting patiently for you just ahead. You're still lying there in the dark, and somewhere in your mind you imagine drifting above a swirling cluster of galaxies. Their combined mass tugs at space-time so deeply that the light around them bends like warm glass. You watch beams curve into arcs, distorted into crescents that wrap around invisible wells. This isn't light being slow, it's light being obedient. It moves straight, always. But the space it moves through refuses to stay straight with it. General relativity tells us that gravity isn't a force pulling on light. Instead, gravity reshapes the stage itself. The shortest path between 2 points, what light always follows, becomes a curve when space-time warps. So even at its unbeatable speed, light must follow longer roads. And in a universe filled with massive structures, clusters, filaments, dark matter halos, those roads twist, fold, and stretch in ways that make light's journey far from simple. Astronomers rely on this gravitational lensing to detect things they can't see directly. Telescopes like Hubble and JWST have photographed galaxies smeared into luminous arcs, revealing invisible mass in between. When the first Einstein rings were discovered, scientists realized that galaxy clusters could act as cosmic magnifying glasses. Yet behind the beauty of these distortions lies another truth. Every detour steals time from light, slowing its arrival not by altering its speed, but by lengthening the universe beneath it. You picture a researcher calibrating a gravitational lensing simulation. Code scrolls by in dim light as they adjust mass distributions, test assumptions, rerun maps of dark matter. Their model produces multiple distorted images of the same galaxy, arriving at different times because their photons travel different routes through warped spacetime. The universe becomes a labyrinth, and light becomes a traveler navigating corridors that twist according to invisible architecture. Even our own Milky Way creates measurable delays. Photons passing near the galactic center follow slightly curved paths, stretching their journey by fractions of seconds. It seems trivial until you scale upward. A massive galaxy cluster can delay light by thousands of years compared to a straight route. In the cosmic race between information and expansion, these distortions matter. Light is fast, but the maze it traverses keeps adding more hallways. As you imagine these delays accumulating, you feel the universe becoming textured, full of pockets where gravity gathers and valleys where light sinks slightly deeper before rising back out. The cosmos isn't a smooth, empty arena. It's a relief map sculpted by mass, and light must trace every contour. In powerful radio observatories, scientists measure these delays by monitoring distant quasars. The light flickers irregularly, and when multiple lensed images arrive at different times, astronomers track the offsets. They use this to measure the Hubble constant, one of the most important numbers in cosmology. But the data is noisy, seductive, and hard to interpret. Light arrives late, gravity lies in wait. And telescopes must decode which path each photon took. There's something strangely emotional in imagining a photon splitting around a massive cluster, half of it taking a longer path, half slipping through a shorter curve. They reunite only in the detector on Earth, separated by years or even centuries of delay. And yet they began as the same act of starlight, sent out with no awareness of the maze awaiting them. You might picture light as a message whispered across billions of years, its tone slightly altered by the landscape it crossed. A stretched word here, a softened syllable there. Cosmic delays become the faintest form of poetry, messages shaped not only by their source, but by everything that stood between. Dark matter, mysterious and invisible, plays a key role in this labyrinth. Its gravitational influence outweighs ordinary matter 5-to-1b, sculpting vast cosmic webs. Light bends around these unseeable structures, revealing their shapes indirectly. In a way, the universe's fastest traveler is also its most diligent cartographer, tracing the curves of what cannot be seen. In underground labs, physicists try to catch dark matter particles using detectors chilled to near absolute zero. They wait for the smallest vibration, the faintest collision. Most nights yield nothing, just silence. Yet the gravitational evidence is undeniable, carved into the paths of photons crossing the cosmos. Light becomes the witness that testifies, again and again, that something unseen is there. You start noticing how this theme echoes beyond physics. Even in your life, paths rarely stay straight. You take detours, curve around obstacles, learn from the bends rather than the direct routes. Light isn't weak because its journey is warped. It's resilient because it keeps going despite the distortions. Sometimes, gravitational lensing magnifies galaxies so distant that their original light left before Earth even formed. We only see them because a massive cluster happened to sculpt space-time just right, bending their photons toward us. Without that distortion, they would remain invisible. Sometimes the universe delays light, and sometimes it delivers a gift, an unintended window into the past. Yet these gifts come with reminders. For every magnified galaxy we can now see, others are bent away, hidden entirely. Space-time isn't generous or cruel, it simply follows mass. Light adapts as best it can, but the larger the structures grow, the more the universe resembles an intricate maze, and the more time light must surrender to navigate it. In some regions, near black holes, gravitational time dilation becomes extreme. Although light still moves at the same speed locally, the steepness of space-time makes its escape outward feel agonizingly slow to distant observers. It's like watching someone climb a hill that grows taller beneath their feet. Even light cannot outrun such gravitational depth without paying a toll. You imagine hovering above a supermassive black hole, watching photons orbit dangerously close to the event horizon. Some complete multiple loops before escaping. Others fall inward, erased from future visibility. The choreography is beautiful, but it's also deeply revealing. The universe allows light to be swift, but not sovereign. In imaging the black hole in M87, scientists used an Earth-sized radio array, the Event Horizon Telescope, to capture the now famous glowing ring. That ring is composed of light that took absurdly warped routes, delayed, bent and rebent by gravitational pull. It's extraordinary that light survived those distortions at all, yet it did, reaching Earth after 55 million years. You sense that behind every cosmic image is a story of endurance, photons navigating gravity wells, crawling across expanding space, taking the long way simply because no other way exists. And yet they arrive, maybe late, maybe stretched, maybe quieted, but they arrive. As gravity continues shaping these twisted roads, another question begins to take form, one that whispers through the widening silence of the cosmos. Even if light could avoid the curves of space-time, could it ever keep up with something that stretches the very fabric beneath its feet? A question waiting just ahead, soft and insistent. You picture yourself drifting far from home, somewhere in a quiet pocket of intergalactic space. There's no glow from nearby stars, only faint murmurs of light traveling across the void. In this silence, distance feels like a living presence, stretching, yawning, expanding in every direction. Even at the speed of light, the emptiness feels impossibly wide, as if the universe keeps placing itself just a little further out of reach every moment. Astronomers realized long ago that distant galaxies aren't just sitting in space. They're being carried away as space itself expands. Edwin Hubble first noticed a trend. The farther a galaxy is, the faster it appears to recede. The universe wasn't static, it was stretching. And this stretching created a strange consequence. Some galaxies recede faster than light, not because they break physics, but because space pulls them along like a river widening beneath their feet. You imagine light trying to cross this river, moving fast, unwavering, but always chasing a shoreline that retreats faster than it approaches. When we say a galaxy is 40 billion light-years away, it doesn't mean light took 40 billion years to reach us. It means the fabric between us stretched so much that the numbers themselves became slippery. What used to be close is not close anymore. What used to be reachable is now beyond any hope of illumination. JWST often captures galaxies from the early universe, their light traveling nearly 13.5 billion years before reaching us. But here's the paradox. Many of those galaxies are now more than 30 billion light-years away. Light simply can't cover the new distance that expansion created. The photons we see today were emitted when the universe was young, before the cosmic river accelerated. We are looking at messages that survived the narrowing window of visibility. In research centers, cosmologists run simulations of universal expansion. You picture them staring at screens filled with color-coded filaments of cosmic structure. As the simulation plays, the clusters drift apart, their distances swelling faster and faster. The code shows a horizon, a boundary where galaxies slip beyond sight forever. Not because they vanish, but because no photon they emit today will ever outrun the expanding fabric between us and them. There's a soft sorrow to this idea. Light tries endlessly, but the universe pulls away more quickly each moment. Even the brightest events, supernovae, gamma-ray bursts, quasars blazing with more energy than millions of suns, can't shout loud enough across an expanding cosmos that keeps stretching the stage beneath the players. You might imagine the universe as a breath that never fully exhales, always expanding, easing outward, relaxing into more space. And light is the tone drifting through that breath, crisp but increasingly diluted. Eventually, some tones fade, not because they dim, but because the stage widened so quickly that the sound can no longer reach the edge. The expansion isn't uniform, though. Some regions swell more rapidly than others, leading to structures like cosmic voids, vast plains where galaxies are rare and distances balloon dramatically. If you were floating inside one, you'd feel the emptiness turn almost visible, as if space itself carried tension in every direction. Scientists measure expansion through redshift, the stretching of light into longer wavelengths. A galaxy receding at incredible speed paints its light redder and redder, until some shift past what our instruments can detect. It's like a voice drifting into a lower and lower register, eventually slipping below hearing. In the early universe, expansion was slower, but dark energy, another mystery woven into the fabric of reality, accelerated everything billions of years after the Big Bang. When astronomers discovered this acceleration in 1998, the news rippled through physics. Light wasn't losing speed. Space was gaining ambition. You imagine researchers adjusting data from supernova surveys, comparing brightness curves, correcting atmospheric noise, calibrating redshift catalogs. The discovery emerged not from one perfect measurement, but from the combined whisper of thousands. That whisper said, "The universe is speeding up, and light is falling behind." If you compare cosmic expansion to a rising tide, then photons are tiny boats paddling furiously but drifting steadily backward. The strange part is that the boats never slow down. They remain swift, determined. It's the tide beneath them that grows wilder. There's something oddly human in this imagery. You reach towards something, you move quickly, you try to bridge the distance, but sometimes the distance grows too fast. There are people you lose not because you walked away, but because the space between your lives expanded on its own. Yet even in this cosmic discouragement, there's wonder. We can only see the early light from ancient galaxies because expansion once allowed photons through before closing the door. The system didn't fail us. It gifted us a window briefly open, long enough for the first messages of the cosmos to slip through. The farther out we look, the younger the universe appears in our view. Expansion stretches not only distance, but time itself. In the deep field images of JWST, you aren't seeing galaxies as they are. You're meeting them at ages they left behind billions of years ago. Light tries to carry the present, but arrives holding the past instead. Imagine standing on a shoreline during low tide. The ocean slowly pulls away, leaving behind shells, driftwood, and remnants of things that once drifted close. Cosmic expansion behaves the same way, revealing the universe's distant history while sweeping its present farther and farther away. Observatories like the Vera Rubin Observatory prepare to map billions of galaxies to track how expansion evolves. Each dot in its catalogue becomes a marker of how far the universe has stretched. And somewhere in that data, scientists hope to understand why the cosmos accelerates in the first place. Sometimes the distances become so large that language falters. Billions of light years, trillions, horizons that grow as you approach them. You feel a soft ache in the concept, but also a strange comfort. If the universe expands ceaselessly, then everything in it is sharing the same long drift. When light becomes too redshifted to measure, it doesn't disappear. It slips into wavelengths so long and stretched that they blend into the background whisper of the cosmos. The night sky absorbs those ancient messages quietly, folding them into a kind of cosmic dusk. You imagine lying beneath that sky, aware that much of the universe is already gone from view, not destroyed, not hidden maliciously, just carried away by a fabric that moves faster than illumination. And while you breathe in the dark, you can feel the gentle humility of that truth. It might seem discouraging that so much slips beyond our sight, but in a way, distance is simply the universe's reminder that discovery is never finished. Expansion ensures that the cosmos will always hold something beyond reach, something still unfolding. And as you rest here, listening, there's a sense that the universe hasn't finished revealing what it means for light to fall behind, not just because of distance, but because of something subtler, woven deeper into the unfolding of reality, a quiet hint that the real reason is waiting somewhere the eye can't follow yet. You picture yourself floating above a quiet, moonless landscape, where nothing moves except the faint shimmer of distant stars. In your stillness, a curious sensation rises. It feels as if space itself is subtly curved beneath you, guiding the starlight into graceful arcs. Even here, with everything so calm, gravity is quietly sculpting the paths that photons must take. Light doesn't glide through a perfect void. It winds through a universe that bends around mass like a river around stones. Einstein first imagined this when he proposed that gravity wasn't a force pulling downward, but a curvature of space-time itself. Light has no mass, yet it follows the contours of this geometry. When a massive object warps space-time, photons shift their course. For the first time, humanity understood that light isn't merely fast, it's obedient. It travels at its maximum speed, yet it cannot ignore the shape of the road beneath it. You imagine a beam of light trying to take the straightest path possible, only to find the fabric beneath it dipping gently toward a galaxy, tugged by invisible contours. The photon doesn't slow down, but the journey stretches, lengthens, detours. In cosmic terms, this means light isn't always late. It's sometimes delayed by the very architecture of the universe. One of the most beautiful expressions of this comes from gravitational lensing. Massive clusters of galaxies can bend light so dramatically that they create arcs, rings, and mirrored illusions of distant objects. JWST has captured galaxies stretched into crescent shapes, as if smeared across the sky by an unseen hand. Those shimmering arcs aren't accidents. They're testimonies of how deeply space curves. Astronomers lean close to screens displaying Hubble Deep Field images, searching for faint distortions in the background. A slight curve here, a warped streak there. These are clues. By measuring how much those shapes bend, they reconstruct the invisible mass of dark matter holding the cluster together. Light reveals what it cannot see directly, but only because gravity molded its journey. You imagine yourself suspended near a galaxy cluster, hearing nothing but the silence of intergalactic space. If you watched a photon approach from a distant quasar, you'd swear it changed direction in mid-flight, gliding around the gravity well like a leaf carried by a swirling eddy. The speed never changes. The path does. Light becomes a dancer, performing choreography dictated by mass. Consider the Einstein cross, a quasar whose light is bent into 4 separate images by a foreground galaxy. Those photons left their origin billions of years ago, all at the same moment. Yet they arrive at Earth across different paths, staggered in time. Some reach telescopes years after others, even though they began as one. Gravity turned their journey into a series of layered timelines. In the early 20th century, scientists tested gravitational bending during a solar eclipse. They traveled with delicate photographic plates, fumbling with telescopes and timing as the moon briefly erased the sun's glare. When they compared the star positions before and after the eclipse, they saw the deflection Einstein predicted. Humanity had confirmed that light was not invincible. It was guided. Imagine the technicians brushing dust from the plates, aligning them with careful fingers, holding their breath as the faint star images revealed a subtle shift. Not much, just a fraction of an arc-second. But that tiny shift meant everything. The universe wasn't the stage we thought it was. Light wasn't traveling over flat ground. And the cosmos wasn't simple distance plus speed. In a sense, light is always taking the scenic route around gravity wells. When photons encounter massive objects like black holes, the detours can be extreme. Some light loops entirely around them, once, twice, many times before escaping. What should have been a straight journey becomes a spiraling pilgrimage, adding billions of years to its arrival. You picture yourself near the edge of a supermassive black hole, watching a star's light wrap itself around the darkness like silk caught in a whirlpool. The photon still races at 299,792 kilometers per second, but its path curls endlessly. It's fast, but it isn't free. Geometry governs its fate. Scientists capture these spectacular bends with arrays like the Event Horizon Telescope. They stitch together data from observatories scattered across Earth, forming a planet-sized lens that reveals the silhouette of a black hole. The famous orange ring isn't the black hole itself. It's light, trapped in detours, orbiting the abyss before slipping away toward us. The delicate dance of lensing also lets astronomers study galaxies too faint to see directly. Their light is magnified by foreground masses, stretched like reflections in a curved mirror. Without these cosmic deformations, entire eras of galactic formation would remain invisible. Gravity slows the path of light, yet that delay becomes a gift, offering glimpses of what would otherwise be lost. Sometimes the bending is so extreme that light takes multiple centuries-long paths to Earth. These time delays allow scientists to measure cosmic expansion, refining our understanding of how fast the universe is stretching. Ironically, the distortions that slow light help us understand the expansion that outpaces it. You imagine lying back in your bed while these distant cosmic dances unfold overhead. The creases in space-time are beyond your senses, yet the knowledge that light must navigate such a complex terrain adds a softness to the night. Nothing moves in perfect lines. Everything is shaped by everything else. Even everyday starlight, the kind that reaches your window on a quiet night, has endured tiny bends and curves. Each photon carries a journal of detours, slight or dramatic, stitched into its journey. You never see the effort, only the glow. There's something humbling about knowing that photons endure these challenges just to show us what exists out there. They don't arrive late because they fail. They arrive later because the universe sculpted their road with every mass it ever formed. And as you rest, the idea settles in your mind. Maybe the speed of light isn't the full story. Maybe what slows illumination isn't speed at all, but the shape of the cosmos itself, draped and folded in ways we barely understand. And somewhere inside those folds lies another truth about why light can never quite keep up, a truth that reveals itself when you follow the curves even deeper. You imagine yourself floating in a dim region of space where everything feels slow, not because motion has ceased, but because time itself seems to thicken. Even the stars appear to shimmer with hesitation, as though their light must push through a medium more abstract than matter. Here, in this quiet nowhere, you begin to sense a truth physicists have wrestled with for decades. Light doesn't just face obstacles in space. It faces limits written into time. Einstein's equations hinted at something almost mystical. If you try to accelerate anything with mass toward the speed of light, time for that object begins to stretch, distort, and slow. It's as if time resists the attempt. And if you reach for a perfect massless traveler like a photon, something astonishing happens. Its experience of time collapses entirely. From the photon's perspective, no time passes at all. You picture a photon leaving a star millions of light years away. To you, the journey takes millions of years. But to the photon, the departure and the arrival are the same instant. A single note played twice in the universe's vast cathedral. Light isn't merely fast, it glides along the very edge where time becomes meaningless. This strange behavior creates a problem for anyone hoping to outrun light. To move faster than a photon, you'd need to experience less time than the photon does. But the photon already experiences zero. There's no time left to remove. You can't go below nothing. The universe seals the shortcut by collapsing the clock. Quantum field theorists often describe light not as a traveler but as a disturbance, a vibration in a field that propagates at a fixed speed because of how the field itself is structured. Space doesn't allow faster oscillations, in the same way a guitar string won't vibrate beyond certain harmonics. The limit isn't arbitrary. It's woven into the geometry and tension of space-time. Imagine lying on your back with your hand resting on your chest, feeling your heartbeat. The beat sets its pace. Even if you try to rush it, your heart refuses to go beyond what keeps you alive. Light behaves similarly within the cosmic fabric. The universe has chosen a pulse, the speed of light, and everything aligns itself around that rhythm. Scientists test these ideas in particle accelerators. You can picture the long tunnels of CERN, the humming magnets, the cryogenic chambers hanging like glowing ribs of a mechanical giant. Protons whip around the ring, nudged again and again by electromagnetic pulses. They get so close to the speed of light that gaining a little more speed requires enormous energy. The particles don't accelerate much faster. They just get heavier, dragging more inertia behind them. A technician rubs frost from a viewport, checking alignment. Data streams through consoles as beams collide. But no matter how powerful the machine becomes, the particles never break light's limit. The accelerator isn't failing. It's hitting the universe's built-in wall. This barrier isn't just technological, it's conceptual. Faster than light travel would scramble causality. Effects could occur before causes. Signals could travel backward in time. The sequence of events, the very logic of existence, would unravel like loose threads slipping out of order. Light preserves meaning by defining what can follow what. You imagine light as the universe's narrator, speaking at its own pace. If anything else spoke faster, the story would twist into paradox. Entire timelines would contradict themselves, collapsing into impossible knots. Light isn't fast enough to reveal everything at once, because the universe insists on coherence. It refuses to let reality speak over itself. Even in astrophysics, this limit appears in strange ways. Near neutron stars, objects so dense that a teaspoon would weigh billions of tons, space-time stretches and slows. Clocks near their surfaces tick dramatically slower than clocks far away. If you hovered near one, the world beyond would race ahead. Light must navigate this uneven tempo, slipping through regions where time itself pools like thick syrup. You imagine standing on the crust of a neutron star, your body weight magnified a billionfold E, watching light crawl upward from its surface. To the photon, nothing has changed. It still experiences no time. But to an outside observer, that same photon appears delayed, struggling through the star's intense gravitational time dilation. The universe doesn't slow light, it slows time around it. And in the early universe, just fractions of a second after the Big Bang, conditions were even stranger. Temperatures soared, forces merged, particles popped in and out of plasma like bubbles in a boiling pot. Time behaved differently then, not as a smooth arrow but as a fluctuating field. Light flowed through those primordial conditions, shaped by laws that were still crystallizing. Experiments like those at Fermilab investigate these early time conditions. Scientists study cosmic microwave background maps, detecting faint temperature anisotropies, microscopic variations that hint at how time and space expanded differently in different directions. Light from that era carries fingerprints of the moment the universe decided how fast it would allow anything to move. Quantum mechanics complicates things further. Photons exist in superpositions, sometimes appearing to take multiple paths at once. Yet even in these abstract realms, their maximum speed holds firm. Whatever path light takes in the quantum maze, whichever slit it passes through, whichever state it assumes, its top speed never shifts. Uncertainty rules everything except the limit. You imagine a photon slipping through a double-slit experiment, its probability cloud shimmering across the detector. Scientists adjust mirrors, isolate vibrations, cool the apparatus to near absolute zero. But no matter how delicate the experiment becomes, the universe never lets the photon outrun itself. There's something poetic in that restraint. In a cosmos filled with extremes, black holes, quasars, violent collisions, there remains a single constant that everything orbits: the ceiling speed of information. Light protects the universe from chaos by refusing to move faster. And while you lie here in the dark, listening, it's easy to feel how that constraint mirrors human experience. We often wish we could get somewhere faster, heal faster, learn faster, become who we want to be sooner. But reality unfolds at the pace it needs, not the pace we imagine. Progress moves through the curves of life, not in straight lines. Yet light's limit isn't just a restriction. It's a boundary that shapes beauty. The night sky glows because photons arrive in their own time. Galaxies form structures because gravity competes with that limit. Stars ignite and die, sending messages that take just long enough to reach us when we're ready to observe them. The speed of light defines everything you know: distance, time, causality, structure. It's not fast enough for the universe, because the universe keeps inventing ways to stretch space, distort time, bend geometry, and push boundaries. Light tries to keep pace, but reality expands with deeper ambitions than speed alone can fulfill. And as you rest with that thought, time seems a little softer, as if the night itself is pausing to breathe. Somewhere in this softness lies another layer of the story, one that isn't about speed or distance at all, but about how the universe hides its deepest workings behind the quiet shimmer of illumination. You imagine yourself drifting in a region of space so empty that the nearest atom feels like a distant neighbor. It's a silence deeper than any earthly quiet, almost like a vacuum not just of matter, but of meaning. Here light behaves strangely, not because it slows down or gets tired, but because the environment becomes so sparse that photons barely interact with anything at all. In this immense emptiness, light's presence begins to feel more like a rumor than a reality. Physicists call these vast expanses cosmic voids, enormous regions stretching tens or even hundreds of millions of light years across. They aren't just empty. They're emptier than anything your senses can imagine. In these voids, gravity loosens its grip, temperature drops toward eternal stillness, and light seems to pass through without touching anything that might slow it down. Yet, paradoxically, it still fails to illuminate everything. There's simply too much nothing. You picture a single photon entering one of these voids. Its journey is effortless, like sliding across glass. But the trip is long, so long that expansion begins to stretch the space around it. Each meter ahead of the photon becomes slightly farther away than the meter before. So even in perfect emptiness, the universe creates an obstacle, not by placing something in the way, but by widening the path beneath its feet. Astronomers studying these voids use galaxy surveys like SDSS, mapping where clusters form and where the great empty regions lie. When you see the cosmic web rendered on a screen, filaments glowing with galaxies, knots forming rich clusters, and the dark spaces between them, you realize light's challenge isn't always obstruction. Sometimes the challenge is the vast loneliness of its route. You imagine researchers adjusting fiber optic spectrographs, collecting redshifts from galaxies lined up like pearls along cosmic filaments. Each data point reveals where matter is. The voids reveal where light has almost nothing to bounce from. By observing these negative spaces, scientists measure how fast light thins into insignificance. As light stretches through these voids, its wavelength lengthens as well. A photon that starts its life as visible light may emerge as infrared, then microwave, eventually fading toward radio frequencies. The emptier the space, the longer the photon travels. The longer it travels, the more the universe stretches it. So even though nothing blocks the photon, the cosmos still drains its energy until it becomes something you can no longer detect. You imagine this wavelength stretching like a sigh that grows softer over time. The glow of a distant galaxy turns into warmth, then into a whisper, then into a silence so wide that only sensitive radio dishes can detect the memory it leaves behind. The universe doesn't extinguish light. It transforms it into subtle echoes. Radio astronomers listen to these echoes using giant dishes like the Green Bank telescope. Their receivers hum with faint signals, picking up photons that have survived billions of years of stretching. You imagine technicians checking cryogenic cooling systems, calibrating their receivers at dawn, listening for traces of light that passed through emptiness most of its life. But the voids don't only stretch light, they also distort your sense of scale. These regions expand faster than denser areas of the universe. More space forms between the sparse particles, pulling everything apart faster. Light can't accelerate to match the stretching. Even at full speed, the path expands faster than it can cross. You imagine watching distant galaxies retreat, their motions exaggerated in this vast emptiness. It's almost as if the void itself inhales, drawing everything outward, leaving light to chase a finish line moving faster than it can sprint. Even the brightest photons cannot close the gap. Dark energy intensifies this expansion. While its nature remains unknown, its influence dominates the large-scale behavior of the cosmos. In regions devoid of matter, dark energy works without resistance, accelerating expansion and amplifying the pressure on light's journey. It's like a wind pushing light backward, though the photon never changes speed. Scientists build numerical simulations to study how voids grow. Code runs overnight on massive supercomputers, calculating how space dilates across billions of years. The voids swell like cosmic lungs, expanding into their full capacity. Light is simply swept along in the tide, unable to gain a foothold. You imagine a technician reviewing simulation outputs, lines of code cascading across a dark screen. They pause at a visualization, showing regions where light becomes nearly undetectable, places where photons are so stretched that they resemble nothing familiar. These are the frontier zones, where the universe becomes too wide for illumination to keep pace. But even within these emptinesses, tiny fluctuations exist. A stray atom, a wandering neutrino, a speck of dust. The photon dances past them, but those minuscule interactions might reveal stories. Scientists analyze deviations in cosmic microwave background maps, seeing how voids leave tiny cold spots. Light becomes a tracer, mapping the universe not just by what's present, but by what's painfully absent. You imagine lying in bed, thinking about these silent expanses. The voids are so large that if the Milky Way were placed inside one, it would look like a lone lantern suspended in a vast, hollow cathedral. Light from that lantern might travel forever, yet never illuminate the far walls. These regions remind you that emptiness isn't passive. It shapes the universe actively, stretching photons, expanding horizons, and defining where visibility ends. Even with nothing to hinder it, light still loses ground to the universe's widening breadth. Sometimes the most powerful force working against light isn't matter, or gravity, or relativity, it's scale, the sheer immensity of distance. The way the universe prefers to grow, not stay static. Light is fast. The cosmos is vast. Vastness wins. Yet there's a strange serenity in that imbalance. If the universe were smaller, tighter, more orderly, we'd have fewer mysteries to unravel. Expansion creates the unknown, and the unknown fuels curiosity. Light is not fast enough, but its struggle allows us to witness the tension between illumination and obscurity. You picture all these ideas settling quietly around you, like dust floating in a sunbeam. In the deepest voids, light finds its limits. But those limits tell us something delicate and profound. The universe isn't designed to be fully seen, and somewhere beyond these hollow expanses, another challenge waits, one that doesn't come from emptiness or distance, but from the strange way that space itself shifts under the influence of invisible forces. A challenge that bends not just light, but the meaning of fast altogether. You picture yourself drifting through a space so small you can't measure it with ordinary thought, far below atoms, below nuclei, down into the realm where distance itself becomes uncertain. Here, movement feels different. Even if you hold perfectly still, reality flickers and shivers around you. This is the quantum field, a restless ocean where particles appear and vanish, and where light must navigate not a smooth highway, but a vibrating maze. In this microscopic world, photons don't glide through perfect emptiness. They scatter off fleeting fluctuations, virtual particles that live for impossibly short moments, but still shape the path light takes. Space at this scale isn't clean. It's foamy, unpredictable, filled with jittering potential. Light keeps its incredible speed, but the road beneath it quivers like a drumskin. Quantum electrodynamics, QED, describes these interactions with exquisite precision. Every photon interacts with the vacuum, even when traveling through nothing. Scientists run calculations involving loops, renormalizations, and diagrams filled with virtual electrons and positrons. These aren't obstacles like planets or galaxies. They are tiny flickers of existence, altering how far a photon can go before its identity blurs. You imagine these fluctuations like brief sparks in a dark room. They appear and vanish too quickly to be seen, yet they leave signatures. They polarize the vacuum, shift energy levels in atoms, and modify how light behaves. Even the speed of light itself depends on these quantum rules. It isn't simply fast because the universe said so. It's fast because the structure of the quantum field allows no alternative. In labs, experiments measuring the electron's magnetic moment or the Lamb shift confirm these subtle effects. You picture scientists adjusting lasers, cooling atoms to near absolute zero, aligning detectors with subatomic precision. Even in these controlled environments, nature whispers that emptiness contains layers of structure. The path of light trembles with constraints shaped by fields we cannot directly perceive. The Casimir effect offers a glimpse of this unseen landscape. When two metal plates are placed extremely close together, they experience a force pushing them inward, caused by differences in vacuum fluctuations on each side. Light waves that don't fit between the plates are excluded, creating a pressure imbalance. This is the vacuum squeezing. This is emptiness creating motion, and all of this shapes how electromagnetic waves behave. You picture these plates suspended inside a polished chamber, sensors humming in the cold air. A scientist observes the plates draw together by mere nanometers, an unbelievable movement caused not by machinery, but by the restless jitter of the vacuum. Light must travel through a universe built from this restless state. The photons never slow, but the environment dictates how they propagate, how they transform, how they reach observers across cosmic distances. Virtual particles cause a kind of drag, not a classical drag that slows an object, but a quantum resistance that shapes the boundaries of what waves can exist. The universe doesn't allow faster-than-light waves, because the fields cannot support modes that propagate beyond their natural speed. Light's limit is not chosen, it's inherited. As you drift deeper into this quantum scene, you begin to feel the scale mismatch. The speed of light seems enormous on human scales, but on the Planck scale, the scale of quantum gravity, it is just one of many constants dancing in a delicate balance. If these constants shifted even slightly, stars might not form, atoms might not hold together, and light itself might behave differently. The Planck length is unimaginably tiny, yet it represents something profound, the scale where space-time loses continuity. Below it, space may no longer exist in the way you understand. Light, which depends on the structure of space-time to propagate, cannot meaningfully exceed its own limit because space itself becomes undefined beyond certain frequencies. Physicists try to probe these depths using high-energy particle collisions. In places like CERN or SLAC, beams accelerated to near light speed slam together, releasing energies that briefly reveal hidden rules. You imagine detectors filled with crystal layers and silicon tracking modules, analyzing cascades of particles. Every event whispers clues about how light interacts with the vacuum, but no matter how energetic the collisions become, the laws hold. The maximum speed of information remains the same. Not because nature is stubborn, but because exceeding that speed would require accessing states of space-time that do not exist within our physical reality. Quantum entanglement complicates the picture. Entangled particles influence each other instantaneously, hinting at a kind of superluminal connection. But this influence carries no information, no usable signal, protecting the cosmic speed limit. Light remains the only messenger, and the universe ensures it can never be outrun by anything meaningful. You imagine a pair of entangled photons created in a crystalline chamber, their polarizations linked across space. A researcher measures one, the other reacts instantly. It feels like cheating, like teleportation of information, but the data itself doesn't travel faster than light. Reality keeps its narrative intact. Wave function collapse happens without speed. It's not a journey, it's a revelation. And revelations do not transmit messages. So even here, at the strangest edges of physics, light's limit stands untouched. At cosmic scales, quantum effects blend with relativity. Photons traveling through the intergalactic medium interact with sparse electrons and magnetic fields. They scatter, shift frequency, or convert into hypothetical particles like axions. These processes aren't obstacles, they're gentle nudges. But when repeated over billions of years, they subtly modify the pace at which light reveals the universe. You imagine a photon beginning its life in a quasar's heart, bursting from magnetic maelstroms around a supermassive black hole. It leaves with a specific energy, but billions of years of interactions lower that energy, stretching the wave, dimming the glow. Light remains swift, but its meaning transforms along the journey. Some theories propose that space might have a granular texture at tiny scales, like a mosaic too fine to resolve. If so, photons moving through it might experience tiny delays, accumulating over cosmic distances. Experiments using gamma-ray bursts attempt to detect these delays, measuring arrival times down to fractions of a millisecond. So far, results show no violation of light speed, but the search continues. You picture astronomers monitoring gamma-ray detectors, adjusting time-stamping systems synced to atomic clocks. Their goal isn't to break physics, but to understand whether space-time hides imperfections that affect how light travels. Every null result strengthens the idea that the speed of light isn't merely fast, it's fundamental. The deeper you travel into quantum physics, the clearer it becomes that the universe hides layers of reality that light must obey. The limit isn't imposed from above, it emerges from the fabric of existence. Light is fast enough to illuminate the world you can perceive, but not fast enough to outrun the rules that define perception itself. As you rest with this thought, a peculiar calm settles in. It feels as though the quantum tremors that shape the photon's journey also shape imagination, inviting you to consider that the universe is far more intricate than any single messenger can reveal. And somewhere behind these trembling fields lies an even stranger reason for light's insufficiency, a reason that becomes visible only when you zoom out so far that quantum flickers blur into cosmic patterns. You picture yourself drifting far above a tapestry of galaxies, watching them shift positions as though painted on a living canvas. But something about the motion feels off. They aren't merely moving through space. Space itself is unfolding beneath them, like cloth being pulled in all directions. In this sweeping motion, you sense a quiet truth. Light reveals the universe, but the universe doesn't wait for light. Over billions of years, galaxies rearrange themselves into filaments, clusters, and walls. Vast superstructures emerge that no single photon could ever track continuously. The universe evolves too quickly on grand scales for light to offer a complete picture at once. By the time a photon arrives from a distant galaxy, that galaxy may have changed shape, collided with neighbors, or faded entirely. Astronomers using JWST and Hubble often remark on this frustration. They point telescopes toward ancient light, studying baby galaxies just forming. But they know the structures they observe no longer exist in that form. Light brings history, not presence. The universe's evolution is too fast for illumination to capture in real time. You imagine a researcher scrolling through deep field images, highlighting galaxies at different redshifts. Each redshift is a timestamp, a moment in cosmic history. Light presents these moments like shuffled pages of an old diary. No matter how carefully you arrange them, the story remains incomplete. The universe has lived far more moments than photons can deliver. Meanwhile, entire cycles occur outside light's reach. Dark matter filaments shift and pull on galaxies, sculpting their orbits without emitting a single photon. Dark energy accelerates the cosmic expansion, stretching the canvas faster each billion years. These forces work silently, reshaping reality while light struggles merely to record what the universe looked like long ago. You picture vast cosmic collisions, clusters merging, galaxies passing through each other, stars flung out into intergalactic space. Most of the energy in these events radiates not as light, but as gravitational waves. Light is fast, but not universal. It captures only one flavor of cosmic change. Much of the universe evolves in channels light cannot access. LIGO and Virgo detect those invisible vibrations. Scientists gather in quiet control rooms, watching screens flicker with signals from black hole mergers billions of years away. These waves travel at the speed of light, yet carry information light could never transmit. They reveal motion, mass, and distortion that photons cannot encode. You imagine a technician tightening a mirror's suspension wires, adjusting lasers in vacuum tubes stretching kilometers underground. It takes an extraordinary instrument to detect the whisper of space-time shaking. Light helps measure the waves, but the waves themselves come from realms where illumination fails. Neutrinos move through the universe with barely any interaction. They escape from stellar cores, carrying information light cannot retrieve. When a supernova occurs, neutrinos often reach detectors before photons, because light must emerge through layers of collapsing material. Even in speed, light loses the race. You picture a neutrino observatory buried deep beneath Antarctic ice, waiting for faint flashes of Cherenkov radiation. When a neutrino interacts, it produces a brief cone of blue light, a subtle greeting from particles that outrun photons in revealing stellar deaths. Light arrives late to its own stories. Meanwhile, the expansion of the universe continues relentlessly. The Hubble constant, the measure of cosmic stretch, seems to shift depending on how far back in time you look. The universe evolves so dynamically that even its rate of expansion refuses a stable answer. Light brings clues, but the puzzle changes before those clues arrive. Galaxies now recede faster than they once did. In the future, more and more of them will cross the cosmic event horizon. Light from those galaxies will never reach us, not because photons slow, but because space expands too fast. Light races, but the finish line retreats forever. You imagine yourself drifting at the edge of this horizon. Beyond it, galaxies vanish not by collapsing, but by slipping into unreachable distance. They're still there, alive, evolving, but no light from them will ever meet an observer in our region of space. The universe hides its own pages simply by growing. Even within our observable region, time introduces misalignment. Galaxy clusters evolve, stars ignite and die, black holes merge. By the time we observe light from a distant region once again, the events we detect are already ancient. Light gives us postcards from a universe that has already moved on. Simulations like Illustris or Eagle try to reconstruct the universe's evolution. They fill supercomputers with billions of particles representing dark matter, gas, and stars. These simulations produce breathtaking visuals, spiraling galaxies, expanding clusters, cosmic webs. But even these models admit limitations. Light never delivers enough real-time data to reconstruct the exact story. You imagine programmers refining their models, adding new algorithms for star formation, adjusting turbulence equations, refining dark energy parameters. The simulations evolve, the universe evolves. But light only shows fragments of the truth, snapshots with centuries, millennia, or eons missing between them. There's beauty in this incompleteness. Light gives the universe a kind of poetic privacy. You don't get to witness everything at once. You receive moments distilled, delayed, interpreted. The cosmos keeps some of its movement hidden, not out of secrecy, but because illumination simply cannot keep pace with change on scales this vast. And while you rest, a curious thought flickers in your mind. Maybe the insufficiency of light isn't a flaw. Maybe the universe is more elegant because of it. Without delay, without distance, without tension between illumination and evolution, the cosmos would feel flat, less mysterious, less alive. Light reveals, but reality outruns revelation. That tension gives the night sky its depth. Stars shimmer, not just with brilliance, but with history. Galaxies glow not just with energy, but with time. As you lie in the quiet, you sense that something deeper still lies behind this imbalance. Something not about distance or evolution, but about the strange way the universe decides what can be known and when. a truth that begins to take shape only when you step past light entirely and listen to the silence beneath it. You lie there in the quiet, letting the last pieces of this long journey drift through your thoughts. Bit by bit, the story of light settles into focus, not as something weak or incomplete, but as a messenger doing its best within a universe that refuses to stay still. You've followed photons across stretching space, bending gravity, trembling quantum fields, and horizons that retreat faster than any signal can chase. And somehow, through all this complexity, light still manages to bring you a sliver of the cosmos. As you breathe, you begin to feel how strange and beautiful this limitation is. Light isn't fast enough not because it's lacking, but because the universe is astonishingly ambitious. Space grows, time warps, matter bends, horizons move. The cosmos reshapes itself faster than illumination can carry its stories, and that imperfection becomes its poetry. Light shows you the past with devotion, even knowing the present has already slipped away. You might think of the galaxies you've imagined tonight, those ancient spirals, those faint arcs stretched by gravity, those distant clusters already drifting beyond the cosmic horizon. Light tried to bring them to you, to place them gently in your awareness, even though they've long since become something else. There's a melancholy in that truth, but also a grace. The universe gives you glimpses, not ownership, and while you rest here, the scale of everything feels softer. The speed of light, which once seemed impossibly fast, now feels human in a strange way, limited, earnest, persistent. Its delay mirrors the delays in your own life, the way understanding comes slowly, the way clarity arrives only after long stretches through uncertainty. Light doesn't rush, it simply travels. This journey also traced the hands of the people who study the sky. Astronomers aligning mirrors, technicians calibrating detectors, physicists running simulations, all trying to understand realities that slip just beyond the boundaries of what light can show. Their effort becomes part of the universe's story too. Through them, even the faintest photons find meaning, transformed into knowledge we pass forward. As you sit with all these layers, the cosmic, the human, the personal, you notice how peaceful it feels not to demand completeness. The universe is unfinished everywhere. Light brings what it can. The rest unfolds without needing to be witnessed. There's comfort in understanding that you do not need the whole picture to feel at home here. You might even find solace in the idea that the night sky is not the universe as it is, but as it was. Every star is a memory. Every galaxy is a page preserved from a chapter already rewritten. And somehow, receiving those memories is enough. It's a reminder that presence can exist even when distance stands in the way, and connection can persist despite unreachable horizons. So as you settle deeper into your pillow, your room dim and quiet, you can let go of the pressure to grasp every detail. Not even light achieves that, and light has had billions of years to try. The mystery isn't a flaw, it's the fabric of reality. It's what gives depth to the darkness, warmth to the glow, meaning to the silence between stars. If this long drift through cosmic ideas helped you feel a little calmer or a little less alone, I'm grateful you shared the night with me. And if you'd like more journeys like this, more quiet explorations of the strange edges of the universe, leaving a like and subscribing helps this little corner of the cosmos reach others who might need it too. Before you go, if you're still awake, I'd love to know where you're listening from and what time it is for you right now. There's something comforting in imagining people scattered around the planet, each under their own sky, drifting through the same story at different hours of the night. And as the last of this tale settles into silence, imagine light traveling endlessly through space, not fast enough to reveal everything, but always moving, always trying, always offering its glow to anyone who waits in the dark. In its persistence, you might feel your own kind of strength, and in its gentle delay, perhaps you'll find permission to rest.